All right, greetings everyone. Welcome to the sixth edition of Digital Underground Connect. This is a public service announcement to optimize your experience on Demio. So let's jump right into the interface. So in the middle of the screen, what you see is the presentation slides. Above the presentation slides are video footage of the presenters presenting. So starting from the top left, where the Demio icon is, at the right-hand side is the runtime for the webinar. At the right side of the screen, you will see little bubble icons of fellow attendees. And at the right side of the bubble icons is a cogwheel. This cogwheel icon is for you to manage your video and audio options. Right, and the right-hand side of the Demio interface is the chat option. If you have any questions, be it technical or content-wise, please feel free to ask it in the chat window. Or if you have any opinions or comments, feel free to ask in the chat window. And that is about it. Rob, I hand it over to you.
Right. Thank you, Ray. And also on behalf of myself, a warm welcome from Singapore to the sixth and third all-virtual edition of Digital Underground Connect. Very happy to be joined today by two speakers who will talk to us about what it means to have or to not have access to good information on the ground, geotechnical information, and how we can use technology, leverage technology to really enable everyone to benefit from this wealth of information that everybody is using and working with. Indeed, as Reggie mentioned, we have a chat, so that's our means of interacting with you, the audience. So if you have any remarks, questions, or you just feel like you want to introduce yourself, please do so in the chat. Any questions to me or to the speakers, please just put them in the chat. We as admins have the opportunity, the ability to mark them as questions and answer them at a later point in time. So thank you for that. And with that, let me start with a brief overview of today's schedule. Starting with some news updates from Digital Underground and Digital Underground Connect in Singapore, followed by Prof. Harry Tan, who will share his own wealth of experience working in various geotechnical works and projects and sharing his view on why ground information or geotechnical information is so important. And then he will be followed by Dr. Roger Chandler from Bentley Systems, who will share a bit about solutions and opportunities for cloud-based geotechnical information management. We will close off this session with a brief discussion. So the two speakers will join the panel together with Mr. Jakub Wachocki from Bentley DAA to discuss some questions. So starting off, let's introduce ourselves briefly. So who is it behind DUConnect? So let me start on the top. There's Dr. Victor Koo, Director of the Survey and Geomatics Division of SLA, long-time advocate of reliable maps in Singapore, previously on the, above ground, but now moving towards the underground, and a supporter, of course, of the Digital Underground project and this community of practice as well. There's Jakub, who will introduce himself. Actually, Jakub, can I ask you to briefly take the mic and introduce yourself to the audience?
Everyone, welcome to this Digital Underground Connect, number 6. This is the 6th event of the series. My name is Jakub Wachocki, and I'm heading up the Digital Advancement Academies and our industry advancement programs. And yeah, I hope you enjoyed the session. We're looking forward to this insightful presentation, and to also, understand a bit more how the underground geotechnical data feeds into the rest of the underground information to be able to present and hopefully connect a fully enabled and comprehensive digital twin for underground assets. So I'm looking forward to the rest of the presentation.
Right, thank you, Jakub. My name is Rob. I'm leading a project called Digital Underground here in Singapore at the Singapore ETH Center, which is closely affiliated with ETH Zurich in Switzerland, towards the goal of achieving a reliable map of underground utilities in Singapore. So underground, but a little bit more specific, focusing on one type of asset. Nonetheless, we all have the big view in mind of a digital twin of the underground, which contains more than that. And I think that's also why it's so good to talk about other types of data and information, as we will do today. And last but not least is Reginald Go, who's supporting us technically to make this all a reality, this session. So that's us. And let me start with a quick first announcement, is that we will actually be joined by a new member of the leadership team. I'm very happy that I can announce this, that we are partnering with the SISV, the Singapore Institute of Surveyors and Valuers, to bring DUConnect forward, and specifically Mr. Chua, who's of course a member of the council, the Land Surveying Council of SISV, but also a registered surveyor in Singapore himself, will join us and help shape this. And you know, this is good news for us, because surveyors are extremely important and as the ones who are capturing the data. And I'm really happy that that through this initiative we can really work on something that I think both organizations think is important, which is the capacity of the people in Singapore to be able to deliver good data of good quality for all kinds of purposes. So I'm really happy to announce this. And then also, that was us. Let's talk a bit about who you are. So this is the snapshot that I took about a few hours ago of the registrations. Happy to see a very large representation from Singapore. I think currently is actually almost up to 70% due to some last-minute registrations. Also quite a good representation from Asia in general, and of course also some other countries where we have a few representatives. And to learn a little bit more about who you are, or how you have, if you have anything to do with geotechnical information, let me now share a quick poll with you. And of course, feel free to answer it and tell us how you interact exactly with geotechnical information of the underground. All right, so I see the answers come in. So there's an interesting mix so far. Okay, there's one person now that's saying other. All right, so we're seeing quite a balanced representation, both people that are collecting or capturing the data, using it, consuming the data, working on solutions to use the data for analysis, for example, or be involved in the policy and coordination. And of course, for others, yeah, if you have anything to share, please do so, of course. So great to have you all here. So let's talk a little bit about DUConnect. I'm sure most of you know a little bit what it is by now. So we are a community of practice, and we aim to contribute to better subsurface information, utilities in particular, but not limited to. And we want to create a platform where professionals from various domains, from various backgrounds can come together to talk about this, not just, you know, through contracts, through formal agreements, but really in an honest, you know, open dialogue. This is what we said about 1 year ago, and I think this still holds true. Specifically, we are about learning, sharing knowledge, improvement, so facilitating exchange of information, but also trying to get better each other. But of course, also just meeting each other and get to know each other a little bit better and have a good time while we do all of this. We've had 5 sessions so far. This is number 6. And as you can see, we've touched on quite a broad range of themes related to digital twins or data of the underground. Brief recap on our past events. So this was 2 months ago. We had 2 speakers from the UK, from the National Underground Asset Register, share the results of their project. And fantastic turnout, good audience as well. And some good lessons learned. Interestingly, even though they have built a technical platform, a lot of the success is in engaging stakeholders. Because sharing utilities is not just about getting it done technically, it's also just about getting support. And some very other key lessons that we have identified. Second announcement is that in 2 months' time, we will have a 7th edition of Digital Underground Connect, and already very happy to have Dr. Jeff Zeiss join us to share about his studies on reducing damage to underground utility infrastructure due to excavation. Very interesting to us. You know, as Digital Underground, we are also mostly interested in knowing where things are underground. And Dr. Zeiss is as an independent consultant, but also happens to be our recently joined advisor of our own project, is probably one of the most knowledgeable people on this subject on mapping underground utilities, from everything from the technology to the policy level. I'm really happy that he has agreed to join us within 2 months' time. So please save the date and we will send you an announcement in due time. And then our third and final announcement is that we are going to launch something new. So as you may know, this is a virtual event. This is not because we choose it to be, but obviously because we don't have a choice because of COVID-19. Although we feel that we've extended our outreach and really managed to connect globally, we do feel, you know, we want something more, especially from our local side. We need this engagement in Singapore. We want to solve problems at a local level and have this conversation. And that's why we will launch something we have now dubbed as a working title, Conversations. The idea is basically that we want to establish small working groups or mini projects, call them as you like, in Singapore, with representatives from, could be surveyors, contractors, government agencies, solution developers, anyone, and preferably a good mix, centered around specific challenges that require this broad community to be involved to solve this problem and work towards tangible outcomes. And what we can offer here is, of course, is a series of sessions that will run parallel to our webinars. And the active support of our team, which means our network. We will actively facilitate the sessions and document the progress, but of course also perform any background studies, for example. So the topics are still yet to be decided, but this is really a call to you when you're based in Singapore and you feel this is something you want to contribute to let us know. So I've launched another poll. By the way, this one is private. It shouldn't be visible to anyone else. But if you know already right now that you want to participate in such a conversation, and we do require a small commitment of your time, of course, to do so, then let us know and we'll get in touch with you. So this is really our proposal to engage our local community a bit stronger in the near future. And I really hope that you are also enthusiastic about this idea and identify those challenges that we can solve together. So that brings me to the content of today's session, where basically I think we hope to learn two things from our speakers today. One from Prof. Harry is really, as I said, you know, feet on the ground, years, decades of experience in working with geotechnical information, using it, and also reflecting a bit on what it can deliver and what would go wrong if you wouldn't have access to that information. And of course, the second question is more on okay, if we know what the value is, how can we really unlock that value? How can we you know, be able to benefit from that information to the fullest? And of course, for that, I hope that Dr. Chandler will enlighten us a bit. So with that, let me stop my own sharing and start with the introduction of our first speaker. So Prof. Harry Tan Siu An has been a staff member of the Department of Civil Engineering at the National University of Singapore, or NUS, since May 1980. He has published over 200 technical papers covering topics such as deep excavations, pile foundations, geosynthetics, ground improvement of soft clays, and land reclamation in journals and various international conferences. Prof. Tan has been an intensive user of the Plaxis software since 1992, and he was actively involved in leading courses in industry since 2000. He has taught the use of plexis all over the world in Singapore, Malaysia, Korea, Thailand, Hong Kong, China, India, Australia, and the Netherlands over the last 20 years. And quite recently, he was awarded the GOSS, or Geotechnical Society of Singapore, award for Outstanding Geotechnical Engineer in 2018 for his sustained contributions to education, research, and practice of geotechnical engineering in Singapore. He's a licensed professional engineer since 1994 and a geotechnical specialist since its inauguration in 2007 in Singapore. And today he will talk about the importance of ground information for design and execution of geotechnical works. Prof. Harry, without further ado, the floor is yours.
Okay, thank you. Now, I'm going to share from my own screen so that I can take advantage of the pointer. Now, this is my screen. Let me see. How do I get it enlarged? View sharing option. Okay. Can you all see? DUConnect, share your screen. Okay, this is my screen. Application window. This is the one. Okay, share.
Okay.
Can you all see my screen? Yes, thank you.
We can see it, Prof.
Yes. So I entitled my talk on some site unknowns and its impact on our modeling challenges. What can go wrong? I particularly picked two cases where I was involved as a consultant post the problem, and I was asked to address what actually happened and why it happened and what can be done. And really the root of the two problems, one of the significant factor that contributed to the problems were the unknown site condition, a critical site information that was missing at the point of the initiation of the project. So move the slide forward. Okay. It doesn't move down. What's happening here? Okay, sorry, take some time to respond. So the outline, there are many forms of site unknowns. I noticed that in Digital Connect, Digital Underground Connect, you all are particularly focused on underground utilities, which are more shallow subsurface conditions, buried utilities, man-made kind of facilities. I'm talking more about the natural ground itself, created by nature, by all the long history, the processes of geology. So there are many forms of site unknowns in geotechnical practice. Geotechnical engineering tends to be very much dependent on the local knowledge and local understanding of the local geology and even the local practice. I have many cases to pick from. I picked two cases from the very past distance for obvious reasons. One is most of people who have forgotten about these cases. They're no longer in the headlines, and the parties involved will not be so affected if we were to talk about it in today's context. None of these are meant to put down any parties. All of them had their problems at the time when they were doing this project. So the first one, I want to talk about an unknown foundation type, okay, of a nearby building structure, just next to the diaphragm wall and the excavation. This was one of the location along the circle line. So it's the, I would say, early 2000s. The other one is an uncertain geology for a deep pile foundation to support, the building is 30-story. I dig up the case files to make sure that I got the facts right. 30-story tower in downtown Singapore. And some of the lessons we learned from these two cases. So let's look at case one, an unknown foundation type next to the diaphragm wall. Now, those of us from Singapore, when we see this building, we roughly know where it is. Anyway, it's a condominium adjacent to the MRT construction of a cut cover tunnel works. In fact, it is a station box right in front of this building. The building is not a very tall building, I think only 5-story or so. And it is on slightly higher ground than the road surface here at this level where this construction was going on. And the boundary wall is, of course, those brick interlocking or some kind of brick walls. Well, this is a snapshot of the original design model in Plaxis. I think that time we were using Plaxis version 8, a very old version of Plaxis. In Singapore, when you see a building more than about 5-story or so, your immediate impression is this building must be founded on piles. You all know from Singapore practice, we are a very heavy user of pile foundation. It was said that in Singapore, we have more piles per capita of population than anywhere else in the world. We are really piling country. So this is relatively good ground, Bukit Timah granite, I think. And then what happened is the designer could never really confirm the foundation under this building. It was presumed to be pile foundation. So you see in this Plaxis model where my pointer is, they model pile foundation. Of course, this is a 2D model. At that time, you cannot model the pile foundation quite accurately. So they make use of an equivalent beam element, smeared beam element to model the stiffness of the pile under this building. And the ground was sloping slightly upwards. And this was the station box here. And in those early days, people didn't quite fully appreciate the nature of finite elements. So their models tend to be very complicated. They model the complicated site geology based on all the boreholes. And one of the things you learn about this kind of problems is that in Singapore, because of the right of access, a lot of investigation were done only inside the excavation site itself. Beyond the excavation site, the property doesn't belong to the client or the stakeholder. And so he do not do a lot of investigation beyond his own site boundary. And even the very limited investigation done is usually very paltry and mostly inadequate. So it was quite obvious that in this project, there were no information beyond here. That's why you see horizontal layered soil. Not much information on this side also. And then you have very complicated geologic type of profile in the site itself because they have plenty of boreholes here. So they knew how this formation actually dipped downward and so on. What I'm interested in is to tell you that then when assuming this kind of model, in their calculation, they had no problem doing the excavation, making this station box. I think it's about 15, 20 meter deep, about 20 meter depth. And this building would have been protected by its own pile foundation. There was no problem. But problems arose very early in the project when they simply did the trenching of the diaphragm wall. There's a diaphragm wall here. These two are diaphragm wall for the station box. And this diaphragm wall is quite some distance from the building itself. Okay, it's not just next to the building. And just in creating the trench, slurry filled trench for the diaphragm wall, this building started to tilt. And the tilt was quite significant. You know, you can measure it quite clearly. One end was going down, settled at about 15 mm. We call this point NA, and the opposite end less than 5 mm. So the building started to tilt towards the excavation, and that was a real cause for alarm. Why did this happen? Well, why it's an alarm is very obvious. Your computer model never shows such a tilting, and yet during excavation you see this tilting, and the tilting rate is not insignificant. Well, in order to, the work was stopped for a while. In order to progress in the excavation, they went back to the drawing board. They did their calculation, remodeling, and in their model they still presumed that this guy had tilted. Of course, they now knew how much it tilted, but the mistake they made was they imposed this tilt on the model. That means they purposely use a prescribed displacement to push the footing down by the amount of tilt they see on this side and there's less amount of settlement on the other side. So they impose this tilt on the foundation. Then I ask you to think carefully about this. Is this a good move? Is it correct or incorrect? Wrong. Well, you see by and by why you shouldn't do this. By doing this, they did not capture the real behavior of the natural ground. Why the ground tilted? There was no clear understanding of why this ground caused this building to tilt. And what is important is that when you look at the yielding of the ground, the soil model allow you to look at the tilt in the ground, the yielding. They were using the old Morcolom model. You can see that all the yielded soil was only formed in the front part of the building, okay? Because you enforce it, you push the ground down. So this is like putting more loads on this side of the building than what was the actual loading in the building, okay? Or the building load itself. So something went amiss. I can't get the site to move for whatever reason. Wait, let me try it again. Okay, now I can see this thing. Okay, so it was a wrong yielding mechanism. The actual observed S47 tilt is actually caused by the trenching. But why did the trenching cause the building to tilt? So if the building was on pile foundation, definitely it cannot tilt just because of trenching. It has its own vertical support. So the only obvious conclusion is that this building is not on pile foundation. Using a prescribed displacement to enforce the tilt, in fact, incorrectly modeled this problem and doesn't allow you to move forward, to make any progress in your construction because you would not model the real ground condition. So the subsequent analysis using a prescribed displacement will predict very unexpected results. And I'll show you what this result is. So using this prescribed displacement to enforce the tilt, the resolution or the mitigation measures was to do underpinning. So they're supposed to put in micropiles on the tilted side of the building to underpin the building and therefore stop the tilt deformation. But I'll show you why this is incorrect, because by doing that, they actually created a problem where this building end up showing larger differential settlement just simply by putting in the micropile in the front of the building. So these are two sets of calculation of the same computer model. The one on the top shows you what would happen if you put in a micropile. Point A is at the front of the building, which is closest to the excavation boundary, and point B is at the opposite side. And C and D are another 2 points further down along the building. What you see is if you don't have any micropile, this building, point A, this black line would have come down all the way here till the end of the excavation through all the construction stages. But point B at the back of the building would only come down to this amount. That means that differential settlement actually is not significant, but the whole building will be tilting as it goes. But the differential settlement at the end of the whole project is, if this is about 20 mm, 25 mm, with micropile, they would have stopped the tilting, but they would have stopped the settlement. But you measure, you're going to get a tilt that's about maybe 7 or 8 mm. I can't remember the calculation, but if they had done nothing without micropile and carry on the construction all the way to the end of the project, 300 days later, you actually see that this building, yes, it's going to tilt. There was a big tilt you saw in the front, but towards the end of the project, the building actually more or less settled together using their kind of model. So it doesn't seem logical that with micropile, I'm going to produce a bigger differential settlement, and yet if I did nothing, I see a much smaller differential settlement between the front and the back of the building. So I was asked to review this, and the question is, what would be the correct way to model this problem? You have measurements. So site measurements are very valuable data. One of the first things you got to do is you got to match your observations measured against what you would have calculated in your computer model. That means inside your numerical model itself, your simulated model, you have to model the cause of the tilt of this building right from the start. You got to recapture what actually happened in the ground. And this was done in my model. In this case, I modeled the footing itself. The building was on a shallow foundation, strip footing. And then I calibrate the model to make sure that, hey, I could match the 2 inclinometer that was available in front of the building. And then I did some repeated calculation to refine the FEM model. So the model must recognize the ground reality. And that ground reality is that this building is not on a pile foundation, but on shallow footings. The unfortunate thing is I couldn't understand why no one seemed to have a record of this building foundation. It's not that old a building. Okay? So by modeling now the actual strip footing, and these are all realistic estimate of the actual building loads, then, and this is the cut cover tunnel with the 2 tunnel boring machine that is going to go through, shield tunnel that's going to go through to connect into the station box. You actually could model the problem correctly now, and just modeling in the trenching process itself, having a hole cut open with slurry filled trench, you see this yield inside the model, the yielding of a triangular shape, which is exactly what actually happened to this building. Because of this yielding, this triangular piece of soil yielding into the trench, we get the tilting of this foundation and also the rotation of this temporary CBP wall, which is some distance away from this diaphragm wall. And this is what you see. So the calculations show you, hey, this building is going to tilt towards the excavation. This is even prior to excavation, just making the diaphragm wall trench. And then it's also going to cause the rotation of the contiguous board pile wall. And if my exercise, the actual measurement up to April 2006 were these open circles. And this is the Plexis model that I created. So I could more or less match the I2004 behavior of the first tilt, and then later continuing further up to 2006, where it's going. Okay, a bit of difference here, but this is post-investigation, and same with 2005. On top of this, because they were inclinometer tubes, they also have extensometer inside the tube, which measure the relative settlement of these various points at different levels inside using the spider magnet indicators. And this is what the Plexis model is telling you. This point settled, the point at MX2003 settled in this fashion, and these were the measurements taken later on, and point to MX2004 inside the tube actually show this amount of settlement at about this point. Sorry, I got some coming. So this is where I'm at. Then I examine what would happen if they did nothing, no micropiling or whatever, just carry on construction. So these were all the various construction stages. There are 31 stages. And you can see that as you progress, the tilt get larger, but it is manageable. It's not an impossible tilt. So you are going to get from 20 mm, and the front of the building is going to keep on settling till about 30 mm. And the other side is settled at 5 mm, and at the end of the excavation, towards the end of excavation, is actually 6-7 mm. Then the question is, what is this sudden tilt again towards the end of the excavation, phase 30 and 31? And this really has nothing to do with the excavation. This has to do with the recovery part when they build upward, and I'll show you what happened. This is because this particular structure involved a hole here, the side hole to the station box. And this side hole is going to be supported by a cantilever type wall. And really that tilt has to do with the removal of all the struts inside and the vein shaft and casting in this vein shaft wall and then backfilling the thing. That process itself will cause a permanent 10-meter cantilever wall condition. And it is this permanent 10-meter cantilever wall condition that caused this yielding in front, which is the result showing you that you have this subsequent tilt. another tilt of about 15 mm more, just due to that cantilever support condition, right? So that's where you see the cantilever support condition, this part here. So their model, if you did the wrong model right from the start, you're not going to see this correctly. You're going to see the wrong picture. But when you did it correctly, you're going to see this picture correctly. So the trench instability has to be correctly modeled. Your prediction or your back analysis up to that point must reasonably match the ground performance measurements. Okay. The prediction of future construction then can be made with some credible realism. And then when you do all that till the end of the project, and by the time you have the permanent retaining wall condition with the cantilever type action, you will see a second tilt, but still within controlled condition, right? This is a Plexis 2D model, so we will tend to over-predict the amount of movement. The real movement is more rigid than that because the whole action is actually a 3D action. And a 2D Plexis cannot model the horizontal kind of stiffness support that comes from the real construction. So that's a first case. The first case, the problem is they were not aware that this building was on a footing foundation, this next door building. Okay. Second case, an uncertain geology for a pile foundation to support 30-story tower. A famous building, number 3 Church Street. All right. This building under construction looks like this. This is the finished building. It's known as Samsung Hub. Number 3 Church Street is somewhere near the Singapore River here. All right. Somewhere very close to the, forgot the name of the station, but anyway, it's Chinatown area, okay, somewhere near there, Church Street. So during construction, what is the problem? The original pile foundation for this building was designed based on only 4 boreholes at the 4 corner position of the building. And only 1 borehole was made at the mid-side of one of the shorter edge of the building. So total of 5 boreholes for a 30-story tower. There were no borehole inside the tower footprint because there was some existing structure in there, so it wasn't demolished yet. And then the geologic interpretation assumed that this site is on the sedimentary Jurong Formation. Okay, those from Singapore will understand what is this kind of soil. So it's a sedimentary formation. The bedrock is made of siltstones, sandstones, and sometimes mudstones. But typically they are horizontally or parallel layered beds of sedimentary soils that has become rocks. But this site was really on the boundary between what we call the Jurong Formation and the notorious Fort Canning boulder bed. So the Fort Canning boulder beds are really like Jurong Formation. They are Jurong Formation, Jurong sedimentary material, but they have random large fractions of huge sandstone boulders. These are Jurong sandstone boulders. How did these boulders come about? I'll explain by and by. So this actually makes the pile design concept. The concept based on the first 4 + 1 borehole was totally inadequate. If it had been sedimentary Jurong Formation, they wouldn't have so much trouble with the installation of piles that is designed to penetrate at least 5 meters into hard stratum that is presumably Jurong soil with SPP and blow count greater than 100 blows per 30 centimeter. Well, they started this project in the year 2000, I think, and by the time of the end of construction to the roof of the building started to tilt. I'll show you why how the building tilt and why it tilt. And this tilt became more and more serious with time. So by the end of 2002, the tilt was so significant that they haven't finished constructing the building yet, just the skeleton of the building. They had problem even installing the elevator because the elevator shaft is no longer vertical. They had problem installing the curtain wall. The curtain wall had to be installed on a roughly almost vertical surface, but this building surface was already tilted. So there was a gross inadequacy of the pile foundation. Why did it happen? Well, first, we need to understand the Fort Canning boulder bed. This is a fairly complex geology. What we know of the Fort Canning boulder bed in the early 2000s was roughly this area. You see this shaded area? It came out from a paper by Nick Sherlaw and the LTA people. We somehow know that this area are the area where we have this Fort Canning boulder bed deposits and how they came about. How do we know that this was Fort Canning boulder bed? Because there are a lot of tall buildings built around this area. This is right in the city center, the old city hall. Raffles Place Station is here. So from LTA projects plus all the towers around here, we know that these are areas of Fort Canning boulder bed. Now the Fort Canning boulder bed essentially is boulders that fell off Fort Canning Hill. So Fort Canning Hill was somewhere back here. Somewhere in the geologic past, there was landslides and the boulder rocks, the rocks broke up and was rolled downhill and they formed these boulders. You can see all these boulders embedded inside this orangey material. The orange material is actually your Jurong formation, your Jurong soil, sedimentary soil. So this whole thing is sometimes technically in geology parlance is called a colluvial deposit or colluvial deposit of the old Jurong formation. When there was landslide from Fort Canning Hill, it rolled down into this slope of the Jurong Hill and then it formed this bed of material, which is this Fort Canning boulder bed. And then subsequently, newer formations start to form over geologic time history in the Pleistocene, late Pleistocene era. And you have the old alluvium and the Kallang formation on top of the Jurong formation and on top of this Fort Canning boulder bed. Now, back in the 2000s, then later with more and more buildings and investigation and so on, this little dot, this little bubble here has become a shape like this. And this bubble here has become a shape like this and another shape down here. So this is the knowledge in the early 2000s. This is the knowledge we have today. What a difference. So the unfortunate thing is this Samsung Hub, number 3 Church Street, is located right at this corner. This is taken from Google Map. This is Singapore River, Marina Barrage. And you can see this thing, if you map it into this position here on this D-Star more updated map of where the Fort Canning boulder bed is, you can see that this particular site sits smack right on this boundary, somewhere here. So the 4 borehole, together with the 1 additional borehole at the edge of the building, in fact, the 4 borehole, if anybody who look at those boreholes would think that, hey, you are inside Jurong soils and Jurong rock. You never worry about boulder because you can't see boulder easily in a single borehole. And only 1 borehole had some indication of some small presence of sandstone cores, suggesting that there were broken pieces of a larger boulder. And the problem with the boulders inside the Fort Canning boulder bed is they are multi-dimension, different shapes. Some of them are vertical in nature, some horizontal and so on. So it depends on the luck of the draw. Your borehole happened to go through smack right inside here, you may not even see any boulder. So the engineer who designed this pile foundation assumed his site is Jurong formation site. And why did he assume that? Well, he had knowledge of the building foundation around this area, and it happens that the building at that time were all outside of this boundary. They were on Jurong soil, the towers. So he presumed that his tower will also be on Jurong soil. Now, this is the data taken of this building, I think, if I remember correctly, May 2004. So from 2002, 2004, it keep on tilting, and you can see the tilt. All the material here, all the piles that were seated down here in Fort Canning boulder bed actually were too short. They all show this big settlement of over 200, the high hundreds, 80, 190 to 200 mm settlement. Whereas back here in the Jurong formation, the pile only settled about 100 mm. It kind of got dragged down by the shorter piles in this Jurong Fort Canning boulder bed. Now, this is the court case in 2002. Why I show you this court case? So that whoever saw this, please understand, I'm not putting anybody down. I'm just trying to get the history of the case out in actually the tilt is very small, 0.1 to 0.2 degrees. By that time, Leaning Tower of Pisa already had 5-degree tilt. So this building is in no danger of collapsing. There was no real safety issue involved. But the fact that the building tilted quite significantly, the authorities stopped the building project, made a lot of rectification work. The contractor, Samsung, spent 2 years with very expensive rectification work to try to prevent this building from tilting any further, and better still, to allow the building to tilt back, okay, by putting in stronger and stiffer piles on the zone that has settled a lot more. So these are the experts, Mr. Song himself, myself helping Mr. Song, and then on the opposite side, Harry Poulos and Nick Sherlock. Now, you can read this for yourself, but basically, the building tilted. The people were taken to task by BCA, that includes the contractor Samsung, and the consultant at that time was Moncel. Okay? So these two companies were taken to task. But anyway, the judge ruled in their favor. So BCA lost this case. Never mind, it's a good lesson learned. But the important thing is that, look, this building was built on 73 board piles. With the detailed investigation, we discovered that 66 out of the 73 board pile did not achieve the design intent of having 5-meter socket into SPT N greater than 100 hard stratum. Why did this happen? Okay, and one of the primary reasons is the piling contractor equipment was inadequate. He was using a low power type of machine that would easily cut into Jurong soil, but cannot cut into Jurong Fort Canning boulder bed. So the type of piling machine was not adequate to install this kind of piles inside bouldery beds. You look at the core hole, there were about 50 or 60 additional borehole done to see what kind of soil we are in. These are typical Jurong soil, sedimentary soil, and this is typical Jurong sandstone. And then you see these small little pieces here and there. So from this kind of borehole, I can tell you, you can't tell the difference between a Fort Canning boulder bed and a Jurong sedimentary deposit. Not easy to tell unless you are a very skilled geologist. Now, I did some computer model with my student on this foundation. If you had only used this 5 borehole, you would have created a model on the left here. 4 corner borehole and 1 edge borehole will produce a very simplified picture of the geology of this site. Then, because of the failure investigation, we have more than 40 additional boreholes inside the building footprint. And with that amount of borehole, we put it back into the computer program. At that time, Plexus wasn't very powerful. This was 3D foundation, but it could produce the correct type of geology. You're going to see the kind of layering and so on. And you can see how complex it is. Right at this edge, this corner of the building, we have very deep, soft marine clay, Kalang soil, and then a little bit of the Jurong formation. Then the next thing you know, you are down into the boulder bed. Very, very thin Jurong soil. So that is the gut of the problem. You are into a different kind of ground as against this simplified ground. This was the ground where you had 5-meter socket into this SPT greater than 100 material. Fine, you get away with the thing. And then also there's very thick F1 sand layer, upper marine clay, F1 sand, lower marine clay, and then some of these Kalang, I don't know, maybe all alluvium a little bit, also siltstone, sandstones, and then the Jurong formation, the Fort Canning boulder bed below that. So that is the difficulty. Now, what was so difficult about the retrofitting? By that time, when they discovered the building was tilting, they already reached the roof. The frame of the building has already gone up all the way to the roof, and the floors were also in. So they had very low headroom to do the compensation piling. In fact, this building has another additional 80 over new piles to replace the 73 piles that were inadequate. And these piles were specially made. They were using, they flew in the equipment from Gammon, Hong Kong, special type of low head equipment to give you these 4-meter segments of piles. And we had to actually we call these mini piles. They were short 4-meter section, welded end to end, and you keep augering and pushing them down. Okay, so there are 80 over of these new compensation piles. This is the model of the building. I'm not going to go much into it, but anyway, this is what you're going to see. So if you, at that time, I didn't have a powerful enough plexus to do this correctly, but I did an approximate model. And if you model the actual pile foundation, the equivalent toe of the pile on a straight bed like that, you're going to see a picture something like this. The piles were all too short, 66 of them. And so when the building weight keep going up to the top of the building start to tilt. And that's exactly what happened but this particular building. So you get undesirable differential settlement, about 100 mm at one end, and the other end exceed 200 mm, maybe about 250 or whatever, about 0.1 to 0.2 degree tilt. But it's enough to give you a headache in terms of all your architectural facade. So some simple conclusion. It is not prudent to design a heavy pile foundation when we don't fully understand the ground condition. So the ground investigation with 5 boreholes, none of it is inside the building footprint, is really, really dicey. Okay, it's a very, very risky operation. So insufficient borehole mislead even experienced engineers to make incorrect interpretation of the actual ground profile. So for the case in view, all your surrounding towers, which happen to be on the Jurong formation, they use a simple type of design with 5-meter borehole board pile socket into SPTN into 100. They perform very well. But this building, no, it couldn't work because even it was the wrong machine to try to do these piles. There were other complexity I don't want to mention, but basically the test piles, the 1 static test and the 5 PDA test were not true testing. They were not done correctly, and they obviously did not test the inadequacy of the piles. The one pile that was tested was itself also questionable. So the end result is when the building was constructed to 30-story, just the frame dead load alone caused this building to tilt towards the deeper end of the FCBB. And so it caused another 2 years of delay in construction, very costly remedial compensation piling, and very costly structural strengthening of the building frame. Just to give you an idea, the original pile foundation was priced at about below $1 million, $800,000, which is a real super low price for the pile foundation, the 73 piles. But the retrofitted piles, the additional piling, roughly cost around $25 million, plus all the strengthening, I think another easily $20 million. So you put in another $40–50 million to retrofit this building. So that's the end of my presentation. I'll stop sharing there.
Fantastic. It was very insightful. Now I think we realize how important it is to actually get accurate information about the ground soil that's underpinning our capital projects. And you see the risk of differential settlement in terms of a collapse or tilting of a particular building. Very similar risks apply to tunnels and also bridges. But Prof, before when we were preparing for this webinar, we talked about how much actually money is overspent to design certain constructions with oversized structures due to the lack of unavailability of data generally around soil, which will have also implication in the carbon footprint, given that the cement is one of the biggest contributor to the carbon footprint. So I wonder what would need to happen to achieve those savings. We talk about 10–20% savings. Which data should be available, and at which point of time to enable these savings that we talked about?
Okay, yeah. I think first, the ground profiling is probably the most primary information we need to do a good design. That means the actual layering of the soil is geology and how these different soils are distributed and so on. So that requires a kind of a mapping, underground mapping of the site geology. In Singapore, we have a lot of that information. No shortage of that information in almost any site. But to really take advantage of this kind of information to optimize your foundation design or your intent of your foundation design, it has to go beyond just the ground profiling. The ground profiling itself is the bare minimal information. What is really needed is good geotechnical testing. That is another level. So you need to do enough testing. That includes site investigation testing, in situ tests, lab tests, and most important in pile foundation, the actual pile test itself to see the performance of the actual foundation element. So if we have adequate testing, then we are able to do the good interpretation of the kind of parameters that we can actually get from this material, and therefore we could optimize the design. So this is something that many project owners as well as organizations, two things are always in competition with trying to do this optimization. One is the lack of time. In construction project, time is money. And second is the lack of money. Money in the sense that everybody has this mindset of being penny wise and pound foolish, thinking that if we save money on investigation, we actually save money for the project. It's not true, because the investigation cost is only a small fraction of the total project cost. For example, that Church Street building, that building cost, actual construction cost was only about 100+ million. The total building project, I think, was 300 over million. With 100 over million for the project, they could have easily avoided the problem of what they saw. By the time they saw the problem, they had pumped in almost another 50 million into the building. And the building value was around 300 million. So they could have avoided that problem if they had done the right investigation, but it was not. The investigation was grossly inadequate. 5 boreholes in a very complex site. Yeah. So I think there's a lot of room for good geotechnical engineering in this respect. The number of boreholes plus whatever other in situ investigation, and also better improved testings and to actually allow us to have the numbers and the parameters to make reliable models of the construction before we actually construct. I think these are the two things that I
fantastic. Thank you very much. I think what we realize here is that first of all, collection of data and capturing of data, but also managing the testing data and having it available maybe for the next projects as well, and sharing it across organization from one project to the next project to the neighboring projects and so forth is becoming quite important to avoid, as you could see, huge risks, again, at potentially adding 30% of your overall cost of a project. Thank you very much, Dr. Chan. I will now move to Dr. Chandler, who will talk about some of the projects and some of the strategies in terms of geotechnical information management, who will uncover and show us a little bit about his experience in managing data on underground data on some of the projects, some of the most interesting projects. So, Chandler, over to you.
Excellent. Thank you very much indeed. It's great to be here this afternoon. Let me just share my slides here. So hopefully, yeah, we can see the slides there. So we've got a quick poll question there up on the screen. If you'd like to just reply on that poll, give me an idea of who's on the call and what sort of involvements you've got. So while you do that, I'll just introduce myself. My name is Roger Chandler. I've been into geotechnical data management now for about 25 years, since working as an offshore geotechnical engineer. Fascinated by the collection of data, the storage of data, and really what you can do with it when you've got it. So it's kind of driven me from a geotechnical background into an IT and computer background. Now currently one of the directors of geotechnical information management here, looking at Bentley, looking after products such as OpenGround, Holebase, and Gint. Okay, brilliant. Thank you very much for answering the polls. Lots of people here who have got data and able to query the projects and systems across their information. Quite a few people who don't also have previous data from previous projects. So what we're going to talk about today, we're going to look about how cloud computing possibly, potentially, or already is changing things. And we're going to look at that in a way that we can justify or disprove the statement that cloud computing offers us an opportunity to greatly enhance the digital engineering and improve the way we collaborate. Now, this could be collaboration across a project, it could be collaboration across a region, it could even be worldwide collaboration. So there's all sorts of ways that cloud computing can help us do that. And what we're going to do in this presentation, we're going to look at a couple of areas. First of all, we're going to discuss what cloud computing means in the context of what we're talking about. Cloud computing is one of those terms that can mean an awful lot of things. So we're going to narrow it down in the presentation. And then we're going to see what the benefits are and why projects would use it, why organizations would use it, or maybe why you would use it and utilize it for a regional archive. So hopefully by the end of the presentation, you'll get an idea of how things have changed over the last probably 3 or 4 years, and how rapidly they are changing going forward. We are definitely on a parabolic curve in the way that this technology enables people to work together and enables cool functionality and products to come together. So let's start with the first section. What is cloud computing in our context? So if we have a look at the way a traditional computer program, a borehole logging program or GI, site investigation management program works, we have two elements of it, really. We have the computer at the bottom there, the powerful brain, so a nice fast laptop or desktop, and then somewhere we have the memory, which is a database. And that database may be on a server, or it may be a long way away from your machine. Some programs will actually put the database and the brain in the same machine, in which case you're not in a collaborative environment at all. You are just working on your own on your laptop. So generally that data, the memory, will be put on a server somewhere. Now, when that program requests a borehole log, what it effectively does, it asks that memory lots of questions. So it'll say, give me the geology, give me the samples, give me the water strike information, and then the brain will put it onto a log, which means there's lots of communication going back between the brain and the memory, and bringing that information back. And that could delay things, especially if you're now all forced to work from home, as we still are here in the UK, and when your IT, quite rightly, puts a big firewall in place. You start to see the program slow down. Access gets difficult. You can't get past the security of your IT to actually get through into your own environment to get the data. Everything is really constrained for working within an office environment where you are physically connected with wires or a fast Wi-Fi into that memory. The cloud computing option works differently. And the way this works is that we have a situation where the cloud is now the brains and the memory. So our program at the bottom, when it asks for a borehole log, it goes to the cloud. It says, give me borehole log for borehole 1 on this template, at this depth rate, etc. The cloud then generates the log and then sends that log back down to the computer. Now, this has the added benefit that this computer can be as dumb as you like. It doesn't have to be fast and powerful anymore. It doesn't have to have a major site investigation piece of software on it. It can be done from anything. So now, actually, on our handheld units, we could ask while we're drilling to have a full borehole log. Now, this handheld unit doesn't need to know all the code to create a borehole log. It doesn't have to have a designer application to make your logs and everything else. All it does is it needs to know that literally the 15 lines of code that sends it to the cloud here. The cloud authenticates the user. The log is then displayed. The same with any corporate GIS system, national GIS system, anything at all will now be able to present borehole logs, site plans, sections, 3D models, anything you like, simply by making calls to the cloud. The cloud presents the data, works it all out, sends it back. This gives us tremendous opportunity to do all sorts of cool things. Because one of the biggest things about cloud technology and the way that the cloud technology is usually written is that it's extensible. So we are now looking at a platform, not a product. Okay, so previously you'd have had Gint, or you'd have had Holebase, you'd have had one of the other applications to draw your borehole logs. Now you're looking at a platform. Now this means that other people or you can add to that platform. So if there's missing functionality or there's something that you want to do, you can actually add it in yourself. And you can write code with whatever language that you prefer. That will enable you to bolt things in. And the cloud service that we do here at Bentley now, we have lots of external developers and internal developers bolting in really cool things to allow you to do stuff with your data. Now, this could be anything from desktop applications like the borehole logging we talked about, field data collection systems, it could be monitoring systems, it could be all sorts of things. It could be your internal systems, so your project management systems. We've got some really cool stuff going on at the moment with augmented reality, looking at using augmented reality with your borehole data, and all the way through to Internet of Things so that you can connect your barometers directly into a cloud environment. So the latest barometer data will appear on your borehole logs without any problems going through, without any file transfers or anything else going through. So lots of real benefits, and what we're doing at Bentley and what we're trying to do here within this environment in the cloud is a connected data environment. So this means that instead of going around the circle, you plan it, you drill it, you test it, you present it, you do some Plaxis analysis as we saw in the previous presentation, and then we do some modeling and visualization. We can now jump across a circle anytime we like. So we can be planning as we're drilling. So we can actually have an agile site investigation approach if we like, depending on what we find. We can then go back into the planning stage and communicate directly with the people on the site, or what we're finding from the laboratory testing, or we can do visualization as we drill. So as the drilling crew are on site, we can actually be visualizing that in 3 dimensions in real time. So lots of really interesting ways that this circle now jumps across, and you can do all sorts of things to it. So if we can do all of this, why do people want to use it? Because we need to look at the motivation for people to use this as we go through. And we're going to start with, why would you use it within a project? Well, if we look at that circle within a project environment, within laboratories or offices around the world, they are still very disconnected workflows. So the SI planning, the site exploration, the visualization, they're all bits that work on their own, and there may be some way of getting from one to the other. And companies will have worked on doing a specific way in using data transfer formats and things, maybe between the laboratory testing and the SI presentation. So maybe there's an Excel transfer format or an AGS data transfer format, which I know is popular both in Singapore and the UK. And companies will have worked out how to connect various stages of this journey up using these data transfer formats or methods, but they won't necessarily have put all the blocks together. So for example, if we look back at the example we had a minute ago, we could be on-site drilling. So this is our on-site driller or on-site engineer logging various things, and he literally presses the update button here. And that effectively means that anyone can now view that borehole log either on the web, on the cloud, on their smart TV, on whatever they want. Now, assuming they have security rights to see it, because obviously you don't want everyone watching your driller drilling in real time. So lots of ways to secure your data and application going through. But that connected data environment for a project environment saves an awful lot of money and reduces a lot of errors. So every time we have to retype something, every time we have to transfer it and re-import it, there is a possibility that the data changes or that the data is messed up in some way, either by humans or by computers. So by doing it as this connected data environment, effectively, we all have access, or everyone within the project has access to the current set of data. And really works on that platform basis. As soon as that data is updated, everyone has it. All the drawings update, all the models update, all the borehole logs update. It's as simple as that. Now, there's a great case study on the Bentley website. There's a project here in the UK they call the Lower Thames Crossing. It's a very large road tunnel that's being built in the estuary of the River Thames, just east of London. And they are using a collaboration platform for all their design teams. So they're uploading all the site investigation data, all the borehole data into the collaboration platform, and then various design teams from various consultants are accessing that data in real time. So they're all looking at the same set of data, they're all working on the same information and working through it. So this is a scheme that's alive and well. This is a practice that is becoming more and more common, both here in the US, UK, and around the world. So we've seen some of the benefits there for projects in joining groups and products together. When we look at organizations, this is where it starts to get really exciting, because now what we're going to try and do, we're going to try and join companies together so that companies are doing it in a specific way, and that will help their QA and will help their quality of the work that they're producing as well. So one of the big problems we have with engineers, I speak as an engineer, is that we like to re-engineer things. So we like to make things better. And that generally means that if someone gives us access to a product which we can change things on, we will quite happily change things to make them better. And that's great. And that should be encouraged, but it also should be controlled, because the big problem with that is that we now have 6 really clever, really intelligent engineers in our organization running in 6 different directions. And from a QA point of view or a standardization point of view, that is a nightmare. So when we look at centralizing our model and centralizing our data and centralizing our templates and everything standards, the organizations really start to benefit. So for example, if we look at what's happened when those 6 or 8 engineers have all run away and put all their projects in different locations on the network, they've all got project folders, they've all decided their own structure for project folders, where in fact, if we put it in a central database, we can do more work with it. We can do cross-project queries. We can ask where a certain material type is in Singapore. We can look at that information. Now, if we need to devise a program that goes along and looks at all sorts of Excel spreadsheets or databases in lots of different project files, then that's very difficult, and it doesn't happen, basically. So by putting it into a central database, we then have the benefit of being able to query all of those projects together. And getting some statistical analysis. Now, companies love this because they can even go to the extent of saying, right, what I want to know is how many holes did I drill last week? How many meterage of holes did I drill last week? Joe Bloggs, the driller, what did he do? This project, what did that do? So you can get management dashboards now out of drilling operations or site investigation operations to really do project management of that process as you go through. You've also got standardization. Now, this is a big issue. Not so much in areas of Singapore and the UK where there are standardized formats like the AGS that kind of depict how you look at setting up databases and schemas, but the standardization itself is a big win. So instead of having 21 different ways of doing things because you've got lots of different engineers over time, you can effectively have a central model, and that central model represented there by the dark green in the circle, dark green circle in the center, is pretty much the same for every project. And then additional projects, you may have something slightly different, or you may have an environmental element to it, or there may be something specific you need to log for it. So that is where the standardization comes in. It's a bit like an onion. You have a big center, and then you have some layers on the outside that you can add to it. But effectively, that core being central and being standardized allows you to do cross-project querying and all sorts of other cool stuff as well. Once you've designed something cool, once you've harnessed one of those brilliant engineers to do something really good for one of your projects, that something really good is available for all of your projects. Okay, so now you can really speed up that competitive advantage you've got by employing those clever engineers rather than have them run off in lots of different directions. Now, when we put all our data together, we start to get some really interesting insights as an organization level. So Singapore, I know, is a small place. I know it well. I've been several times, both working and holidaying. And if you've been a site investigation company or you're a geotechnical engineering company in Singapore and you've been around for the last 20 years or so, you have a lot of data somewhere in your library or in your archive, that tells you something about the conditions of Singapore. You also have a great central resource as well in Singapore with the data that they have. So here is a very simple map. It's one of our customers. They work, as you can see, not much in Singapore, but they work a lot in the southeast corner of the UK. The cluster of dots there in the middle of the insert picture is Gatwick Airport, our second national airport, just south of London. Now, if you're tendering against this company for a job around the Gatwick Airport area, you can pretty much be assured that this company has really good local knowledge of what they found going there in the past. Now, this doesn't mean that's what they're going to find this time, and it doesn't mean they don't need to drill any holes, and I think that was perfectly highlighted with the previous presentation. But what it does mean is they're going to go on site, they're going to be designing their site investigation with a lot of background information in the bag, and knowing what they're going to see and what they're going to want to try and find. So this sort of knowledge is invaluable when you're putting it together on an organization level. So effectively, we have centralization and standardization as the two real big benefits for organizations when they move to a cloud environment going forward. Okay, so let's now go into the one that's maybe slightly more controversial, which is a regional archive. When would a regional archive be good? Well, we now effectively have all the tools to release that data into a regional archive. And what the question now becomes is, do we want to, and how do we do it, and what are the ramifications of doing that? Now, the ground we quite often have as a siloed event. So a ground belongs to a building or a structure that we're effectively building, as we saw there with the Church Street example. And that works well for the building until something happens next door. Really good example of this is the Millennium Tower in San Francisco. There's nothing better than upsetting a lot of rich people to get something moving, which is exactly what happened here. They built the condo, which by 2018 had sunk 17 inches and tilted quite considerably as well. So very similar to the case studies we heard earlier. And the main concern was it was actually not caused by the construction of the tower, but caused by the construction of the transit center that was next to the tower, that was built after the tower was completed. So one thing we do know is that the ground is a shared space. Whether we like it or not, people will and can tunnel under us, they can build next to us, and their buildings and tunnelings will have an effect on our structures. So we might not want to share our data with them, but all of a sudden, if actually sharing our data with them stops them doing something that's going to cause problems in our building or our structure, then maybe we want to share data with them. Maybe our relationship with our data is beginning to change and we suddenly see it's actually a liability if we hold on to it and don't share it, rather than actually an asset, saying, look, why don't you have the data of the building next door? Because we don't want you to mess that up by not knowing what's there as well. So if we start to look at the shared space scenario and we start to take it into an extensible platform and ways that we can work together, we could effectively take the archive of Singapore, we could put it into a cloud environment, and we could have all sorts of applications building straight into it, both feeding from it and feeding to it. And all of that data then can be available to whoever the organization in charge of that cloud would like to have access to it. So it's not freely available information. They can, do whatever they like with it. Bentley doesn't own it. Bentley doesn't control it. Nothing like that. It's all owned and controlled by the people who are running and organizing that cloud. Now, a lot of research into Singapore, and I know from with the Year in Infrastructure conference we did in Singapore last year that I was at and presenting, lots and lots of data is available in Singapore at the moment. Now, I pulled one of these slides off a presentation I was reading in preparation for this. And we look at the paper here presented at the DMT in 2018, so a couple of years ago, and looking at the work they did on collecting and cleaning the data, the borehole data for Singapore. And as you can see there on the slide, 48,828 boreholes in AGS format. Now, that should be commended and applauded. That is a superb piece of work that was carried out with this, and now gives you a massive opportunity. if that archive and additional archives can be made available to other projects through a collaboration platform, then we could do all sorts of things with it. But the thing is, we don't know what's going to be done with it. And the one thing we are concerned about is that people are going to use it for the wrong purposes. And that belief that people are going to use it for the wrong purposes usually stops us doing it. But we need to investigate that, and we need to go forward with this idea. For example, if we go back to our extensible platform and we put that Singapore data in the middle. Now, that if we fast forwarded 3 months, 2 months, 1 month, next week, it really wouldn't take that long to have a cloud system available for that data to be. We could then plug universities, we could plug teaching establishments, we could plug all sorts of people into the machine learning arena that is looking and consuming data to try and come up with algorithms to help us work out what we're doing. We could plug it into VR and AR applications, we could plug it into anything else. In fact, if it was available in the cloud, people already working on these applications would be highly delighted and would want to work with you to try and plug their applications into that data going forward. So some really exciting opportunities by taking the data you have and putting it into a collaboration platform, not just at project level or organization level, but at regional level as well. Now, the applications we have connecting into the cloud already, we have quite a lot going through. We have SV Designer, which is one of Bentley's products, connecting in. We have a Plaxis connector in the making at the moment. There's a Leapfrog connector, Leapfrog 3D modeling application from New Zealand. So third-party application here. We also have it connecting into Power BI, and some of the data loggers are also connecting in as well. Tons and tons of internal connections as well to GIS systems and other things being developed as we go through. The system we're talking about for Bentley is the Open Ground Cloud. We currently have 2 regions who are live in Virginia in North America and London. We are also looking to open a Sydney data center shortly. Being cloud, you can operate it from anywhere as long as your data laws allow it. But hopefully when we launch something in Sydney, the speed within the Singapore region will be even faster than it is at the moment if you're running out of London. And it's up and running. We have about 750,000 boreholes in the system. So that gives you an idea. We've been running now for 2 years on the system, and we already have 750,000 boreholes. I've been working in geotechnical software now for 25 years, and I've never seen something take off as fast as Open Ground Cloud has. So it's a really exciting place to be at the moment. The ecosystem is growing, the number of developers are growing, the number of users are growing, and the number of data in the system is growing as well. And the possibilities are exponentially growing. It's really a really exciting place to be. So I'll finish with just a couple of conclusions and allow you to ask questions. So I truly believe that cloud computing is changing the way construction projects, large and small, are collaborating with the geotechnical data. We are benefiting from centralized and standardization approach to cloud technology. Lots of companies with multiple offices absolutely love that approach. And taking away from our siloed data and moving into the power of AI and machine learning will really harness the data in years to come. So hopefully that's given you an idea of what cloud computing is and how it's changing the way people are working at the moment.
Thank you very much, Dr. Chandler. I think what is exciting to see is this rapidly emerging opportunity for everyone to engage with, how can I call it, democratized data, right? Because once you put it in a centralized repository, whatever it is, it sort of becomes available for innovation to happen. And it becomes almost like a platform for new ideas to flourish, so to say. And you mentioned some of opportunities in terms of the artificial intelligence, VR, AR applications, really building on top of this foundation layer. And this sort of reminds me of internet era, when sort of data started to be connected through TCP/IP net connectors, and suddenly you have platforms such as Amazon or other services that became available just because of the connectivity and because of the data became structured and available. So that's really exciting to see. What I would do, I would open up for a few minutes of discussions before we close the session. And also in the meantime, if you could type in any questions you might have. In the meantime, we would like to ask you a question, everyone who is sort of engaged in this conversation, is attending this session. What are the most pressing obstacles towards making geotechnical data available? If you could type in your answer into the chat window as we progress our conversation. So if you could focus on the obstacles in making the geotechnical data available, because as we can see here, we actually have a big dependency. The dependency is people trusting other users of data and putting the data, making it available to other users. So anyone in this chat, if you could type any of the obstacles. But in the meantime, maybe also Prof. Tan, if you could turn on the webcam. What do you think are the biggest obstacles towards making geotechnical data available? Why do you think the geotechnical data is not as available as we would like to?
There is a question of ownership of data. Can you all hear me?
Yes, we'll hear you perfectly fine.
Ownership of data, like the Internet of Things. Data is the new oil. So people are wondering, how do we make money from data? See, so all these big organizations and all these big internet companies, they're all actually mining data. Data is like raw material, minerals. So there is one hesitance of sharing data and information is because we are competitors. We are not collaborators in some sense of the word, and in certain projects where a person has inside information on a peculiar problem in this particular place, he or this organization obviously has the advantage in the tendering process because all the tenders are competitive tenders. So that's one of the reasons why you find it's not so easy to get everybody to share. The people who are most willing to share data are usually the government organizations or government affiliated organizations, because for them, if they can bring down the cost of tenders, it's a benefit to them and the country. So people like SLA, BCA, LTA should not have any hesitance to want to share their data. And you notice that digitization work done by Chujian and all that, all the organizations that contributed data towards them seems to be all these government organizations. You don't get them from the private sector very much. And the other group of people, very difficult to get information from, are the military. They seem to think that everything is top secret. If you know that somebody tunnel underground and build a Ho Chi Minh type of underground village right under your feet. I think that's one of the difficulty, especially where data on private properties end up as private property. They don't easily. Usually, when I ask some consultant or contractor for certain information about a certain site, which I think they have worked on a neighboring site, they will always tell me, say, "Bro, we share this in confidence, but don't tell anybody how you got it, and also don't mention that don't mention us." Yeah, it's strictly confidential. So it's that kind of situation we are in.
So it's great.
I can see the value of what Lee is doing. Yeah, it's great value, but it depends on the mindset. And also, in my experience here, it's strange. The authorities are, to some extent, quite protective of data. Not so much in geotechnical, but in other areas, like traffic data and I think those that has higher impact on the social scene and so on, they are more sensitive about that kind of data, consumer data, and also consumer patterns and all that. Those are very, very sensitive commercial data. So that's why they came up with this legal framework of what PDPA and Protection of Data Act and so on. Data is you can get charged in court for misusing personal data in any way. So I guess there shouldn't be any problem with ground information, but still.
Sure. Thank you very much, Prof. Tan. I'm thinking, so, and you can see that there is a lot of sort of answers as well flowing inside the chat. You will see that a number of people mentioning regulation, liability, security, also cost in terms of organizing and processing the data, and some of the other obstacles. Maybe I will ask Dr. Chandler on this side, how would you address those challenges? What is, I understand there is a certain reluctance in sharing the data, but given your exposure to a number of countries around the world, what do you see of positive happening? How countries are addressing the problem of sort of stinginess in sharing the data?
Well, I think I completely agree with Fostan's comments. Governments should be leading the way with governmental data, which is being paid for by taxpayers. But private organizations will always hoard their data because they conceive it to be valuable. Now, it's only valuable if they are actually using it. Whereas you talk to a lot of, I get the opportunity to talk to a lot of organizations to say our data is valuable. And I say, what do you do with it? And they go, well, we don't really do anything with it. And it's like, well, it's not really very valuable then, is it? It's in a cardboard box somewhere in an archive room. It's not valuable at all. That's a liability. So there's the sharing within organizations. There's a sharing of the company knowledge, which is where most of the online geotechnical data sharing is at the moment. So sharing it within your commercial environment to get that benefit from it. But we are seeing lots of local governments and government-led initiatives coming on and doing that, especially with Department of Transports and things like that, both here in the UK and in the States. I've been working with the Highways England Authority here, where they actually disseminate all of their geotechnical data on a cloud-based system and have done now for about 15 to 20 years. So they have 3 or 4 terabytes of data now that they give to all of their contractors, because they want their contractors to have the maximum knowledge possible before they start to tender for things, because it's going to affect their tender price. Now, some of the other things that you've got there, security. Security is massive. It's top of everyone's list. We get security questionnaires all the time. They run to about 260 questions about what is happening with the data when it goes up. We haven't failed a security test yet. You get through, there was a couple of others, copyright. What happens if someone uses my data incorrectly? Well, it depends who you shared it with and what conditions you had of sharing. The BGS here in the UK has a lot of conditions on the data you can download from its website that says you download it at your own peril. It has nothing to do with us. It has nothing to do with the data supplier. What you do it, you are fully liable for it. And the people who download that data and use it, they will always need to go and collect their own data, because their liability insurance won't cover them for just data they found on the web, so to speak. They need to have proved that that is correct, and the only way to do that is to drill holes. So there's a lot of issues going around it, but the benefits certainly from a project and a company level or organization level are massive, and then from a regional level, if you have something leading the way like you do in Singapore with the BCA and people like that, then there are benefits then to sharing that to a wider community. And what we've seen with the work we've done when you get large data sets from organizations is that academics love it, because they can plug into it, they can put all their fancy new algorithms, and they can do testing on real data. So one of the big problems that the clever, smart university people have is that they can never get data. And one of the problems that the people with data have is they never get smart academics. So it's kind of like, fantastic, let's put the two together while you're in your operational system. So that actually has a real benefit. And I had a meeting on Friday with somebody in the States who was doing some really cool stuff. And I said, why don't you plug it into this? And they went, oh, that's just saved me years. You've now got all the boring stuff I didn't want to do, and I can plug my exciting stuff into it. So yeah, we're seeing that come away, and those barriers that people are putting in, which, I mean, they've pretty much nailed the top 10 of barriers on the chat there. We're seeing those coming down.
So I completely understand, let's say, the potential willingness and also motivation behind central authorities to share data generally, and to make it available to the public, make it more centralized, but also of better quality generally. I wonder what would be the motivation that we could start to establish to make sure that also private entities start to share the data. So I'm not talking about, let's say, the stick motivation in this sense, government authorities requiring you to share the data, which I think is quite useful as well, and I think has its very, very good effect already in a number of countries. But what would be, do you think, the motivations that we could, as an industry, establish to make sure that sharing data is more valuable privately than holding data internally? And you talked about this holding data as being actually not viable, because you're not extracting this latent value within your data, you're just storing it. So what would make it, do you think, valuable and desirable for the companies to share the data, and commercially viable as well? What would be? What do you think? Maybe we start with Dr. And Professor Tan as a conclusive answer before we end the call, and then we move to the conclusive answer from Dr. Chandra, and then later on I will just pass quickly to Rob to wrap the conversation.
Yeah. I think for a commercial entity, we need to go through a process of self-enlightenment. If a commercial company can see how they can benefit from a common database where their data and other people's data are free, available to those who contribute to the database, then that will move the thing forward. Yeah, it is you got to create a win-win environment. I'm not sure how we do that. It cannot always win-win, but sometimes somebody win, somebody lose. But if we can create a common win-win environment, it will definitely open up the way forward to doing this cloud computing stuff, and what Bentley is chasing after, having a project-wise database where it really benefits. Right now, the way I see it, private companies tend to want to see it as they do it within their organization. That means within the organization, they have a lot of data sharing from one engineer to another, from one project team to another, and so on. But outside of the organization is quite limited. Yeah. They're very hesitant because of the many issues that Chandler mentions. It's not so straightforward. Yeah. In fact, every time I work with different companies, they will send me the information on the project through a private channel, and always there's this confidential clause on it that it's strictly for your own consumption and only for helping us in this project, and you're not supposed to divulge this information to any other organization. So it's you take an oath of secrecy when you embark on anything even with the government. They make you sign they have a very interesting form. It's called the Official Secrets Act. So everything that is confidential is official secret, and you can be charged in court for contravening that act, because it's a is an act enforced by the law. No? So when you sign on that dotted line, you zip up your mouth and you kind of blindfold your eyes and said, I only saw it for that moment and that's it. So
Yeah,
it's very quick. Yeah, I can understand. Yeah. So this sensitivity of the timeliness of information is a very it's a very complex problem. I don't have an answer, honestly.
I'm sure that's something that's on the minds of many, and sooner or later, engineers, actually, the word engineering comes from the ingenious, something that can be invented, and therefore, I think we will be able to invent a solution for this very soon. In the meantime, while I'm asking Dr. Chandler the same question, if you can maybe propose your own solution on how to create a win-win situation, commercial situation, where private organizations are willing to share the data as well. So, Dr. Chandra?
Yeah, it's a very difficult question to answer. The stick approach is the way that it always starts, and we have worked on a number of projects where the legislation is the one driving it, or the client is the one driving it, and it's written into the contracts that thou shall share their data on this system. So that's the stick approach that everyone has to abide by. Now, an interesting case study is the Canterbury database for Christchurch. So that spun out of necessity after the earthquakes in Christchurch and the rebuilding of Christchurch. And that started with a stick, and that was thou shall submit AGS data to get planning permission to do anything, including rebuild your house. So they actually got an awful lot of data into the central repository there at Canterbury for that database. Now, that database has now gone nationwide, both North and South Island, New Zealand. And the consultants, I believe, although I haven't caught up with it for the last couple of years, they are all now contributing to it because they saw the benefits of contributing in Canterbury. And the data set that is now available in Canterbury, which is primarily private data of rebuild projects, has proved very valuable. And they have seen that value. And the consultants are now sharing data across the entire country. So in my experience, the only way to do it is you start with a stick, and then people realize how valuable what they've been beaten into to actually do, and then they get on board. I haven't seen a successful case of you getting somebody on board before they've seen the value, and the only way to get the value is to force people to do it. So that's kind of what I've seen work and not work around the world.
Fantastic. So there is just one last question, and I promise we close later on, because it's a very important question about data quality from Victor, who asks about how do we make sure, what are the strategies to ensure that the data is shared of known quality, so we understand who is responsible of the data, and also make sure that the data is qualified to be utilized. Any comments here?
Well,
I think we've come a long way. Yeah, go ahead, Chandler.
Yes, well, there's all sorts of metadata you can put onto data to say where it came from and who did it. And you may know what year it was done and therefore what standards it was done to, or you may know the reputation of the company that did it and therefore apply something into that. I think the better context is to assume that any data that is shared with you is of unreliable quality, and that you have to prove its quality before you use it. That's a much safer way to do it than to say someone say, yeah, this is really good quality data. By the way, what did you want it for? So you've got to kind of really assume that anything that's being shared with you is of dubious quality, and that you're going to prove it before you do anything with it. And at the end of the day, your liability insurance will insist that you do that anyway, rather than designing on past papers or other things that you may be going through.
Yeah, fantastic. Any last closing statement from Prof. Tan about this subject?
Well, I think we cannot turn the clock backward. COVID has shown us how important it is. Timely data availability must be made to everybody who have a stake interest in a project. And I think if we can do that in a transparent and open manner, everybody will be the winner. Really, the COVID crisis just show us that people hiding information and all that just create more problem for others. If everybody had been transparent and true, then we could have imposed the correct restrictions when it's needed, and the problem will not blow up. So it's just crazy. In every area, it can just be more transparent and open in our data sharing, and particularly engineering data, which don't have any real military implication or say security in terms of the country's security. We should make it more available. The only thing I would like to suggest also, I think we are trying it out, is a proper standardization of data presentation, because geotechnical data comes in all shapes and sizes, and sometimes it's almost impossible to make sense of the data. From my own project experience, I mean, I got data from Belgium, and first I don't know their language, and then I use a Google interpreter, and I'm not sure if the Google is doing it right. So yeah, it's painful work to try to understand the data coming from a foreign country.
Thank you very much for these exhaustive answers. I will now leave the stage and give it to Rob, who will make conclusive statements. Thank you very much, everyone, and hope you enjoyed it.
Okay, thank you, Jacob.
And thank you for moderating this. As a Dutch person, I will not comment on the Belgians and their mastery of the language. I have a lot of family there, so I'd better not. Anyway, it's up to me to close this off, and we're well over time. But still, I think a lot of people are tuned in, and there's even a bit of a good discussion going on in the chat, which I'm very happy to see. Let me start by thanking both of you, Professor Tan, Dr. Chandler, for making the time to share your insights, to go perhaps beyond what you usually present, and really open up for discussions and give us your sort of honest views and insights. So I really very much appreciate that, and I would like to thank you very much for your contributions. And I think once again, it made for a really good session with a very very complete storyline, from going from the need, the value, towards solutions that could actually make it a reality. For me, always lesson learned as someone who is into the underground utility mapping domain is that I'm always just so amazed by how much similarities there exist between the two domains when we talk about a conclusion like site investigations always pay off. I think the same goes for subsurface utilities. It always pays off to do a proper investigation, a proper mapping for any capital project in advance. And of course, the same goes again. Any private developer is both a consumer and a producer potentially of good data. And indeed, it's a question of how to get that data from those projects. And again, the same observation is true, right? Maybe it requires a really long-term vision to understand. Hopefully, not as Simon says in the chat, not until we die, right? Hopefully, really realize a little bit earlier that it's just good to share data and not to just sit on it, because it will benefit yourself even in the long run, undoubtedly. So with that, I would like to thank you and the audience, but not before I quickly release the last call to action to the audience, which is to kindly give us your feedback, your thoughts on this event. We really appreciate it. We got a lot of good feedback last time, and I'm always open to hear more about how you think we could do better, because we want to make it better every time, again and again. So thank you all. Thank you, speakers. Thank you, Jakub. Thank you, Reginald, for the support. And thank you, audience, for joining us. And hopefully we will see you again next time around.
Okay, thank you.
Have a good day.
Thank you. Bye, everybody.
Bye, everybody.